You right y'all back with some classical dynamics. I think I figured out what the issue is with the previous problem. It seems like the terminology is just different in this textbook. It says projection of the x value onto x prime and the y value onto x prime. But apparently what it really means is the breaking this vector into xy components and taking the x component and the y component. Well, I guess technically the x component of each. So yeah, technically it'll be the x component of each. So this one is a 13 for the y, and it's still y prime is negative x cosine that angle. Now the only difference is the angles don't match. So I have to ask the professor about this terminology. But nevertheless, I'll see what the next section says. So we'll continue from this. Last time we left off on the matrix form of the transformation. And I'll put a question mark in this area. So we'll see if it's the uh, projection of the xy component. And we were going to start with the example of the next one. So that would be example 1.1. Let's see what that's talking about. Start on the next page. This is a point P represented by x1, x2, x3. Specifically with point 213. In another coordinate system, the same point is represented by P x1 prime, x2 prime, x3 prime. And it says x2 has been rotated toward x3 around the x1 axis. X2 rotated towards x3 around the x1 axis, and theta equals 30 degrees. All right, so this is the illustration they give us. Right? So we have x1, x2, x3, and this is the standard uh, order of coordinate systems. There's always x, y, z. And then we have x2 is rotated towards x3 around the x1 axis. So we have this spinning up this way, and x2 prime, this is 30 degrees. I could say this is theta. So that would have to mean that this is also 30 degrees. Going that way, and x1 is the same. So this is still x1 prime. So I guess technically my idea of doing just two axes was how it's normally done, because technically this is just a rotation in two axes. And we have 2, 1, 3. So I'll call this point P. It's probably not the scale. Our P is represented in two coordinate systems, one rotated from the other by 30 degrees. So we need the lambda ij using the definition of the equations. Lambda ij equals cosine x1 prime x1. So we have the matrix lambda 1, 1, lambda 1, 2, lambda 1, 3, lambda 2, 1, lambda 2, 2, lambda 2, 3, lambda 3, 1, lambda 3, 2, lambda 3, 3. So that's going to be cosine of the angle between x1 prime and x prime, so that's 0. And I remember there was no leading number. It was x1, then the angle between them. So these are just the direction cosines. So this is the direction only. Uh, Cosine the angle between x1 prime and x2, that's 90 degrees. Cosine angle between x1 prime and x3 is still 90. Cosine angle between x2 prime and x1 still 90. Between x2 prime and x2, that's 30. x2 prime and x3, that would be 60. Because this is 90 minus theta. Cosine x3 prime and x1, ninety. Cosine x3 prime and x2, that'd be 90 plus theta, that's 120. And cosine x3 prime and x3, that's 30. So I'll check these and see if that's what they get. 0, 90, 90, 90, 30, 60, even though they still did the cosine of 30. I believe this book has mistakes. It says cosine of 90 minus 30, which is cosine of 60, but that doesn't equal cosine of 30, which they also have. So I have to watch this book. But the answer should be 0.5, which is cosine of 60. Tiny cosine 120. The final answer they have is correct, but they do have some typos, it looks like. So this will be 1, 0, 0, 0, 0.866, 0.5, 0, negative 0.5, and 0.866. So this is the direction matrix, I guess I'll call it. All right, so that adds up. And they have the same thing, 1, 0, 0, 0, 0, 8.66, 0.5, 0, negative 0.5, 8.66. And then So now we can get the actual point. So x1 prime equals x1 lambda 1 1 plus x2 lambda 1 2 plus x3 lambda 1 3. So that equals 2 1 plus 0 equals 2. So all we're doing is taking the row and summing it with the appropriate x1, x2, x3 values. X2 prime equals x1 lambda 2 1 plus x2 lambda 2 2 plus x3 lambda 2 3 equals 0 plus 0.866 times 1 plus 0.5 times 3. And that equals, let's see, 0.866 plus 0.53, 2.366, right? And x3 prime equals x1 lambda 3 1 plus x2 lambda 3 2 plus x3 lambda 3 3. So that equals 0 plus or minus 0.51 plus 0.8663 equals 2.098, which matches the book number. Notice that the rotation operation preserves the length of the position vector. So the length of each one is the same. So the magnitude of P equals square root of 2 squared plus 1 squared plus 3 squared, which equals square root of 2 squared plus 2.366 squared plus 2.098 squared. So let's see. Yep, that is it's almost exact. Of course, I'm sure the calculator rounded some, but they do equal 3.742. All right, pretty good. So this is technically not really necessary to understand that detail I was trying to figure out, but it would be nice to. Um, but we have this worked out. So that was example 1. 0.1. And let's see what we have next. So 1.4. So that's good. We're on to the next section. Properties. All right. To begin the discussion of rotation matrices, we must recall two trigonometric results. Consider, as in figure 1.4a, a line segment extending in a certain direction. So maybe I shall share the book here for this one. All right, so good. I have both of them shared and just pick which one I would like. Oh, well, this is inconvenient because it doesn't show properly. Let me see here. See if I can figure out a good way to show this. That's not. Well, I'll just draw uh as necessary. Trying to work out a different program here. And by the way, if anybody joins, you could join me on Discord if you have any questions about anything. We'll go back to the iPad screen, and we have call figure 1.4.1, a line segment extending in a certain direction in space. We choose an origin for a coordinate system that lies at some point on the line, and the line then makes certain definite angles with each of the coordinate axes. We let the angle made with x1, x2, and x3 be alpha, beta, and gamma. The quantities of interest are the cosines of these angles. The quantities are called direction cosines of the line. The first result we need is the identity, right? So let me draw out what they have here. So we have a regular axis like we drew before, which I could simply copy. Well, actually, it'd probably be better just to write it over. right? So this is x1, x2, x3 of the default reference frame. And we have a line. We'll see this line is coming out here. And we have so alpha coming out this way. So let's say alpha goes here, and we'll say beta goes here, and gamma goes here. So maybe it'd be better to color code it. So this is gamma. This is alpha. This is beta. These lines up a bit if necessary. Trying out this new function on this thing. Doesn't seem to work too well. Apparently I can't lift the pen at all because it goes right back to the previous tool the moment I stop erasing. I don't necessarily always want to erase only once. So let me try it for a little while and turn it off if it continues to not work. Oh, and hold up. It's working properly. I don't know what happened here. Let's see. Okay, my bad. I have to click the proper window. There we go. All right, seems to be sharing properly now. All right, so that's the drawing that we're looking at. And the transformation is going to be here. This will be theta between these two. So this will be, well, and those are the values. So this is at the point alpha, beta, gamma, and this is at the point alpha prime, beta prime, gamma prime. All right, easy enough. So that's figure 1.4 that I mentioned earlier. A line segment is defined by angles, so it is angles. So I guess they're defining the point as three groupings of angles. A line segment is defined by angles that, from the coordinate axes, another line segment is added that is defined by angles A prime, beta prime, gamma prime. The matrix, so hold up. Okay, there we go. Second, we have two lines with direction cosines, cosine A, cosine B, cosine gamma, and cosine A prime, cosine B prime, cosine gamma prime. Then the cosine of the angle theta between these lines is given by, okay, so now we're getting something here. Cosine theta equals cosine alpha prime plus cosine beta prime plus cosine gamma prime. So that's interesting. And that's equation 1.11. So we want so that would, of course, mean that beta equals cosine inverse of all of this. So that's interesting. With a set of axes x1, x2, x3, let us now perform an arbitrary rotation about some axis through the origin in the new position. We'll label the axes x1, x2, x3 all primes. The coordinate rotation may be specified by giving the cosines of all angles between the various axes. In other words, by the lambda ij. Not all of the 9 quantities lambda ij are independent. In fact, 6 relations exist amongst lambda ij, so only 3 are independent. We find these 6 relations by using the trigonometric results stated in equations 1.10 and 1.11. First, the x1, let me check these equations out again. Okay, I guess I missed that equation. So one equation that it gave here is cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. That's equation 1.10. Hmm. All right, I'll go with it. In equation 111 we have there already. First, the x1 prime axis may be considered alone to be a line in the x1, x2, x3 coordinate system. The direction cosines of this line are, so x1 prime axis has directions lambda 1, lambda 2, lambda 3. Technically, that's lambda 1, 1, lambda 1, 2, lambda 1, 3. Yeah, I think I have to turn off this setting here. All right, well, I'll just turn this off later then. All right, similarly, the direction cosines for the x2 prime axis, directions are lambda Ch1, lambda Ch2, lambda Ch3. Similarly, the directions for the x3 prime axis, lambda 3, 1, lambda 3, 2, lambda 3, 3. Because the angle between the x1 prime axis and the x2 prime axis is however 2, is because, of course, we know that the angles between all three of the axes are always 90 degrees. We have from equation 1.11. Okay, that makes sense. Angle between x1 prime and x2 prime. Okay. And the direction is this. The direction is this, and putting this with the other equation, alpha is the angle between x1 prime, no, x1, that's just alpha. So this entire direction thing here seems like it would be that. So that's why they just multiplied the uh, for the directions for the angle of the value between uh, the axes. If I take this equation here, 1.11, so all of these would be 90 degrees, which equals 0, because cosine of 90 is 0. If we were to apply this to uh, between coordinate axes, so the sum of all values j, lambda 1 j, lambda 2 j equals 0. So technically this would be all of these would be prime. And it says in general, for all j, lambda ij, lambda kj equals 0 when I equals not k. So that's the angle between two axes, basically. Equation 1.12a. This is 1.12a. There's three, one for each value I or k of the six relations among the lambda ij. Because the sum of the squares of the direction cosines of a line equals unity, we have for the, why don't they just say equals 1? We have for the x prime 1 axis in the x1, x2, x3 system, x1 1 squared plus x1 2 squared plus x1 3 squared equals 1. Right? Or the sum j of x1 j squared equals the sum of x1j equals 1. So right? So in general, j lambda ij lambda kj equals 1 if I equals k. So this like is basically the direct delta in a different form, I guess. So basically this is the same thing as I lambda ij lambda ij equals 1. So if it's ij, the sum equals 1. If it's different, it equals 0. This is how it pulls out just that single component like direct delta, which are the remaining three relations among the lambda ij. We may combine the results given by equation 1.2 and 1.12b, 1.12a and b. Yep. So it comes up as the sum j lambda ij lambda kj equals the direct delta k, or Kronecker delta, mixing up my deltas. That's the Kronecker delta. So Kronecker delta equals, this was the Kronecker delta, equals 0 for I equals not k, and 1 for I equals k. So I'm still not 100% clear on that, but we'll get there, I'm sure. Right? We're 45 minutes in. This seems like a good break. We start with the Kronecker delta on page 7. So I'll be back later or tomorrow, and we'll continue from here. Thank y'all for joining. Make a like, subscribe, comment, and be sure to join the Discord so you can join live with any questions you might have.